Hello, everybody. Welcome back to lecture 11, which is about thread level parallelism. Sorry, lecture 11. Over here, we'll be discussing, we'll be talking about parallelism, types of parallelism, multi-threading techniques, multi-threading systems, caches, performances, challenges and solutions, and then we'll go over a summary of all of that. Without further ado, let's start with like a brief introduction of parallelism. The whole thing about it is just like understanding like the different type of parallelism when it falls under computer architecture. There's different systems in it. There's a single processor system, and there's also a multi-core and multi-processor system. Importance of that is like it improves performance and efficiency, and it also handles complex and large scale computations. Over here we have a diagram that shows like a very brief what's it called, levels of parallelism. As shown over here, there's like a layer level, an entity level, a function level, an operation level. Each one of them has like a different level that it takes care of, but we'll dig more into the types of systems in the next slide. So without further ado, over here, there's types of parallelism. There's a instruction level parallelism, there's a task level parallelism, there's a data level parallelism, and there's also a thread transaction level parallelism. The instruction level parallelism is pretty much it's a multiple instructions from the same program executed concurrently, and it's also a superscalar and VLIWY architecture. A TLP has different tasks executed on the same data, and an example of that would probably be like database operations. A DLP will be data distributed across different nodes, operated on simultaneously at the same time. An example of that would probably be a matrix multiplication. A thread transaction level parallelism, however, is a multiple process or threads from different programs executed differently. So over here, we also have where it's just like system types and SISD and SIMD and MIMD, which we'll get to later today, how they go through that. But before I get into that, let's talk about what's it called? Alrighty. Let's talk about multi-threading techniques. So there's like a single thread CPU, a chip multiprocessor. There's also a simultaneous multi-threading. So it's pretty much a single thread, a CMP, and SMT. A CMT is pretty much multiple cores, each handling a separated thread. An example of that would probably be an IBM Powered 4. A single thread, however, is only one thread executed at a time, and it limits pipeline hazards, which is an advantage over chip multiprocessors and simultaneous multithreading. Simultaneous multithreading will probably multiple threads executed simultaneously by a single core. So this falls probably like an Intel hyperthreading. Over here we have a diagram just showing the difference between them. Just like we said, a single core has only one core to one thread, pretty much. Direct, there's no multiple threads. However, a single core has simultaneous multi-threading. It goes from one core to like two threads. Next, we'll talk about multiprocessor systems. There are types. There's asymmetric multiprocessors. There's distributed shared memory. And the difference between them is pretty much an SMP is centralized shared memory. A DSM, each processor will have its own unique address space. The models of these programming go underneath message passing and shared memory. Message passing will probably be explicit communication between processors. Shared memory would be implicit communication via shared address spaces. Over here, we have a diagram showing an interconnection network and how like the CPU caches go within that and their inputs and their memory, and also their IOs and their memory at this point. Some key things that we need to talk about in terms of like performance of the multiprocessor system is that it measures in terms of speed up and efficiency, and it also impacts synchronization and load balancing, and sometimes it can be good for the system and how different types of those multiprocessors can have an effect on the system. Cache coherence. So the concept behind it is pretty much ensuring consistency of data stored in local caches and processors. The protocols, though, there's a snooping protocol and there's also a directory-based protocol. A snooping protocol is pretty much a processors monitor the bus for any change. However, the directory-based protocols, those are centralized tracking of shared data. See the difference of that? So that's pretty much for like shared data, and the other one is localized, monitored for bus and any change for the bus and any changes that happens in any bus. And MESI protocol, what is that? That's pretty much modified, shared, exclusive, modified, exclusive, shared, and invalid. Ensures that only one processor can write a cache line at a time. So here on this diagram, we show how it can write and read and how it happens. So like whenever, like all of these happen simultaneously, but whenever they happen, it's made sure that it goes through a cycle, so that way nothing goes in front of the other, and the whole operation keeps going, and the cache coherence operates, and that way it ensures consistency in the data stored in local caches in this processor. Now let's just talk about like a challenge and some solutions for that. So some challenges would probably be inadequate parallelism, communication overhead, and synchronization issues. So inadequate parallelism, limited parallel sections and programs, that's what they are. Communication overhead, there's a high latency in inter-processor communication. Synchronization issues, ensures consistency and avoids race conditions. So all challenges that a processor faces. If there are there are solutions for that. Such solutions have new algorithms, caching and synchronization, as well as memory consistency models. New algorithms in this case probably enhance parallel performance. We can go over this limited parallel sections in our program, just enhance their performance, provide more caching and synchronization, reduce latency and improve efficiency for our communication overhead. For our synchronization issues, we can always have memory consistency models, define rules for memory operations, so that way they can communicate directly and occur simultaneously to ensure consistency. Let's talk about an example over here. An impact of a thread level parallelism, a scenario, probably executing a program with 100 processors. If we were to like have a serial code that we want to find out, and we want to see if it can achieve a speed of up to 80 times that. In order to calculate that after certain calculations, it will probably be only 0.25% of the original code that it can be actually sequential, can be permissible in this analysis. Another scenario would probably be application running on 32 processors with 200 nanoseconds memory reference time. In analysis of that, we're probably performing comparison with and without communication overhead. And the result of that would probably system with all local references is 3.76 times faster. Now let's go over our summary and some key concepts and what are future directions that we can take from this lecture today. So the types of parallelisms and their exploitation in modern systems, we went over that for a bit, and we also went over the importance of multi-threadings and multiprocessor systems, as well as some challenges in parallel processing and some solutions that can be figured out for them. Future directions that we can be taken in terms of this will probably be advancement in multi-threading and parallel processing, also integration of more efficient cache coherence protocols. The importance of this is probably enhancing computational performance and efficiency, as well as addressing scalability and synchronization in multi-core systems. Without further ado, that was today's lecture about parallelisms and their different types and what can fall underneath it in microprocessors. And I'll catch you on the next one. Have a good day.